Hi, this is the little video that I'm going to do on dynamic programming. Now, a lot of the work on dynamic programming you'll be doing in lessons during class time, because it's a good place for you to get an experience of inventing new algorithms using a technique. We didn't even think of doing that for divide and conquer, but for dynamic programming it's quite a bit more possible. Of course, brute force is the easiest place to do that. So let's start by just saying in general that dynamic programming, I won't even waste time writing it. The term it's a famous term that everyone uses, but it's really stupid. It's got a lot of history to it. Like programming used to mean optimization. So we'll be doing problems where we're looking for the best way or the cheapest way to do something. So dynamic programming is really just recursion plus a chart. And the key idea here is to think about subproblems with the same structure. It's the same kind of subproblem, same structure as the original problem. So each cell in the chart for us is going to represent the answer to some question, like what's the best way to do something. And in our chart, each cell will end up pointing to other cells that have already been filled in with answers to other simpler questions. And then these will always be combined in some way to give us the answer to ours. And then we can fill in the whole chart, either on demand or in a systematic, loopy kind of order. Okay, so lesson 8 gives you what you've been working on, and you're probably still working on, gives you some exposure to some of these basic ideas. So I'm just going to do a little bit of that before we jump in and talk about the 0-1 knapsack. And then later, when I have time, we'll do some other problems, including the traveling salesman problem and Floyd's algorithm. And those are a little more involved, but still pretty simple once you get the basic idea of dynamic programming. Okay, so our first problem is computing the binomial coefficient. So a terrible way to do that would be to use the definition. Maybe that's the definition, that n choose k, the number of ways out of n things you can pick k without caring about order, is n factorial over k factorial times n minus k factorial, but that's terrible. So the way everyone in their right mind would do it would be some variation of Pascal's triangle. So Pascal's triangle you're probably familiar with from math class. You just run ones down the outside diagonals in this nice little arrangement, and then as you go along you just add up each two numbers, you add them up to get the number below. So in a sense, the ones are just the one above plus nothing to get another one. So it's a good way to look at it. 5, 10, 10, 5, 1, and so on. So what I was just doing was actually dynamic programming already. So the bad thing would be, just go to another page. 1 was 3 minutes and 30. What the hell's going on? Okay, the bad thing is to directly do it. So if you look at the code on page 46, I won't take time to write it down, but the code is printed out there, and the code just says what I just said. It's like if k equals 0 or n, return 1, and otherwise return the two numbers above. So if you do that with the chart, that's perfectly good, but if you do it with recursive calls, like at the top of page 46, then that's not so good because it blows up and takes a ridiculously long amount of time in an unnecessary way. So that's, I guess, all we have to say about that, because on one of the routine exercises looking at Fibonacci sequence, you'll see the same thing in more detail. Okay, so, and it's a small fact, but you can actually put Pascal's triangle into an ordinary array, with rows and columns as usual, and it's pretty easy. You just, do it in kind of the obvious way. So it's just funny that mathematicians always do the slanty chart where everything's at weird angles. It looks like it'd be hard to implement, but it's actually really easy to implement. Okay, so on to, let's tackle the 0-1 knapsack. All right, so the 0-1 knapsack problem we've already seen. So let's give ourselves an instance to look at. So on page 47, you'll see a little chart. So we've got item number, and we've got the profit of item J, P sub J, and the weight of item J, and we have an overriding number W, which in this example is 12. So the items are 1, 2, 3, 4, 5, and 6. I'm writing these all down quite, but so the profits are 100, 120, 88, 80, 54, and 80, and the weights are 4, 5, 4, 4, 3, 5. So as we talked about before briefly, each item is a unique thing that you might put in your backpack or your knapsack, backpack, or your knapsack to take camping with you, and you're assigning a value to it, which is the so-called profit, and they weigh something. So the constraint is your total weight you can add up is up to 12 units. So we won't, brute force we've already done. I made you write out the chart. So lately we've been talking occasionally about the greedy approach, because it's good for comparison to dynamic programming. So the greedy approach would be to say, look, these guys are actually sorted. These are sorted in profit per weight. I didn't write this column, but if you do the division, you can see, let's see, how many times does 5 go into 120? 24. So these are sorted 24, 22, 20, 18, and 16. So the items 1 through 6 have been sorted, so they're in weight order. We don't really need that. It's good for the greedy approach. We won't actually need it for the dynamic programming. It doesn't help a bit. But so a naive person might say, well, look, use item 1, and then now you've used up 4 pounds out of the 12, so then move on to the next most valuable per pound thing, item 2. At that point we have 4 pounds plus 5 pounds, and then though we have to skip items 3 and 4, which are quite valuable, and use item 5. And if you remember that if you add up those total values, you get 274. The money units aren't necessarily dollars, but we can write it that way. So the greedy approach actually works in this case. So then we get all excited that maybe this is actually a really simple problem. But if we look at embedded exercise 31, which is so tiny it barely deserves to have a label, but if you look at the items, if our items were 1, 2, 3, weighed profit 36, 25, and 20. So that's J, P sub J, and W sub J, and weight was 655. So by taking, so this is a completely new thing. So if we take W equals 10, that's obviously rigged. If you do the greedy approach, you use 6 pounds, use up 6 pounds, get $36 in profit, and then you're done, because neither one of the other items will fit. But if you use both of these items, you can get 55. So you can get 55 money units instead of 36 if you don't use the greedy approach. So that's important. The greedy is not correct. So like in many, many situations, going for short-term optimality doesn't end up being the best long-term strategy. So we're going to talk about a dynamic programming approach now, and that's pretty easy. All right, did I say it was easy? Actually, it's very difficult. No. The reason I say it's difficult is because we have to figure out a chart. So we could do a chart where we said, let's suppose we have some weight J, and we could simply say, we could ask the question is, how did we get to J? how do we get to the winning thing for J? And the answer is, well, we might come from this earlier weight by adding one item. So the problem, this has various problems, so we're not going to do it. It's described in the notes if you're curious. So you can do it a lot like the change making, but it's easier to do a different approach. And the different approach is to use a 2D chart. And in our 2D chart, we'll call it P of Kj is equal to the best profit for the weight under less than or equal to J. But here's the catch: using some items from 1 through K. So in other words, you can't use item when you're on row K of the chart, you can only use items 1 through K. So it turns out so the whole chart is going to be, we're going to have W in the last column, and we'll have all of our items, all in items here. So we can just go through and fill in so what we want is the lower right corner. The lower right corner corresponds to all the weight, W. That's a terrible W. So it corresponds to all the weight W and all the items. So by the time you get to the row N, you're allowed to use all the items. So in row 1, you can only use item 1. So that's a pretty easy one to figure out. And then on row 2, you can bring in item 2 if you want to, and so on all the way down. So the point here is, if you're in row K, column J, and this is a big deal. You'll need, if you understand this about dynamic programming, it'll all be easy and fun. So you've got to always have to figure out or understand, if someone else tells you, how to get the value in this cell, typical cell, in terms of the others. And it's quite simple here, because if you, the row above, so in the cell here that we're target cell, we're allowed to use item K, but in all the cells above we weren't. So this cell right here is one thing to look at. This cell contains the best way to make a weight J, that's the column, given items 1 through K minus 1. So it's possible that's the best you can do. It's possible that using item K doesn't help at weight J. But what if so those are your choices. It either helps to put in item K because that's your new ability, or it doesn't. So the other one, I'm going to erase this now that you've had it to look at for a while. So I want to draw my arrow underneath it. So the other possibility is to go over here. So where is over here? Over here is column J minus W sub K. So what does that say? That says this cell contains the best way to make a weight of J minus WK using items 1 through K minus 1. So this is the most clever way possible to achieve, using that weight as your capacity to which items to use. So if you take that clever thing and now you're allowed to use K, item K, that means this here has one of the possibilities is whatever's in cell P of K minus 1 J minus W sub K, which looks crazy, plus P sub K. So we're taking away the weight of item K when we move to the left column to the left, and we're adding in the profitability. And this other possibility here is the guy straight above, which is just P of K minus 1 J. That corresponds to just not choosing to use item K at this point. We might later when we want to have more weight to play with. But at this cell right here, those are the only two possibilities. You either use it or you don't. If you hearken back to when we did the brute force, we kind of pushed, at least the second time we pushed you that way. So if you're using items 1, 2, and 4, And then there's a question at the next step of use 5 or don't use it, if you remember when we did that. And so this is somewhat the same idea. Okay, so to finish up this little discussion, let's just do the painful chart on page 49, and I'm going to need the whole page for it. Okay, so on page 49 we have a chart, which I won't recopy, but I'm going to try to make a 5x9 chart here. With great skill. I guess I should be using a ruler, but I'm too lazy. Okay, so we're going to make 4 here and 5 here. So 4, 4. I'm using an ancient craftsmanship known as cutting things in half. I usually get it wrong. Okay, so this is the W on the problem on page 49, and the items 2, 3, 4, 5. Oh dear, that was very bad. Oh well. 1, 2, 3, 4, 5. Okay, so they all have various values that you can see on page 49, and so how do we do this? So I'm going to do it starting here. I'm also going to switch to the red for a minute. So from this cell, what do we have to look at? The optimal value right there is that's weight 8, use all 5 items. It's either going to be the guy above or what? So item 5, if we added item 5 to this, we added it to somebody that weighed up to 5 units less. So 5 weighs 1. Okay, hopefully that worked, didn't screw things up. Okay, so we're either going to add it to, so since item 5 sadly only weighs 1 pound, this is the other one. So we're going to look at this cell and this cell. So we're going to look at what's in this cell here and add 12 to it, or we're going to just look at what's in that cell. So one of those two is the winner. So if some magical creature, perhaps a unicorn, had filled in those cells for us, we would be done. Yay. I mean, that's how recursion works and how dynamic programming works. But since they didn't tell us that, we have to look this cell to fill it in. Let me switch colors just because I can. It's possible ways to decide for this cell is the one right above, but now it's item 4. So if we had a really great way to do items 1, 2, and 3, subset of items 1, 2, and 3, if we added item 4 to it, item 4 weighs 2 pounds, so that would be this guy over here. Okay, and then the other one is this guy. So for it, we look straight above, or again from column 7 we go over 2 to column 5. So that cell we could determine that cell if we knew these other 2 cells. And you can see kind of what's happening here. We're getting sort of a scrunched in binary tree. So the next level, I'll go back to blue, I guess. No, I don't know. I wish I had more colors. I'll try red, yellow. So each of these 4 cells, we're going to need, for this far one, we need this one. And let's see, then since item 2 weighs 4 pounds, we have to hop over 1, 2, 3, 4. So we actually need this one. And this one, we go straight above, this one right here, we go straight above and over 4. 1, 2, 3, 4. And this one, we go straight above and over 4. 1, 2, 3, 4. Okay, so you notice there's a little spreading out and overlapping and stuff. So we do have 6 cells here. So I guess it is it's not exactly doubling it. It didn't double because here we had 2 cells on row 4, but when I guess it did. I just was missing it. So yeah, it's not doubling now because of these 4, when you go above and over, some of them overlap, I guess. So there's, oh wait, no, I'm lying. I just missed this one. So we have to know this one is above and then over 1, 2, 3, 4. So wow, it's even worse. There's a question here of whether you should fill in the entire chart or just do it on demand. If you do it with recursion and fill in the chart dynamically as needed, like we did with the Fibonacci, then it's easier to do it that way. Or you can just write a double nested for loop to crank through and fill in all the cells in order. Okay, and finally at the top, it's pretty obvious, I think, we're going to need everybody, right? Okay, so those are the only cells we need to fill in. So let's go back. So now we have to fill them in kind of a first to last order. So right here, in column 0, obviously, oops, sorry. I'm going to try to use a convention, which is we'll put the value in the chart at the top, but then we'll put below it a list of all the items just for convenience. Oh, can't draw with an eraser. So with weight 0, you get 0 in the knapsack. With weight 1, we still get 0. With weight 2, we get 0. Oh no, oh yeah. Because why? Because on row 1, we're only allowed to use item 1, which weighs 3 pounds. And suddenly in column 3, it gets exciting. Now we can make $54 with using item 1. Okay, and then, so am I using an algorithm here? No, this first row is kind of like, it's just the base case. I mean, we can kind of figure it out from scratch, without using any other cells. And that's a good thing because there aren't any cells above. So our recursive idea doesn't work on the first row. So I'm just going to go ahead and work them out from scratch. So with 4 pounds, with a little thought, we can realize that, but we're still only allowed to use item 1. So once we get above 3 pounds, all we'll ever be able to do is, so this is this 54.1 all the way across. So $54 using item 1. And the weight, of course, is 3 pounds. But that kind of doesn't matter in this cell. Okay, now we can go down here. We can ignore this cell because we don't need it. Okay, so now for the first time, so sitting in this cell, let's try to use well, let's start at the right where it's more interesting. If you start from the left, you can kind of delude yourself. Pretty easily make mistakes on the test. So let's start at the far right cell and fill it in. So the choices are $54. You just stick with item 1, or since we're in row 2, we're allowed to bring in item 2. But item 2 weighs 4 pounds, so we'd have to say 8 minus 4 is 4. So it's going to be this 54, it's going to be item 1 plus item 2, giving us 54 plus 64, which is 118. So that's way better. Yay. So that cell we figured out by looking at the 2 above. And we can move from right to left and fill them all in. So why could we do that? We could do that because the total weight was, well, we'll find out. So now in this cell, we look above, and we're 54, or we go over 4, which is 3, so this one also can do 118 and 1 and 2. Okay, from the 2 cells above it, the relevant cells. Okay, and now when we go here, we're either going to do 54 or we're going to go over 4. 1, 2, 3, 4. But when we go over 4, so if we use 4 of our pounds for item 2, then we'll only have 2 pounds for item 1, and we can't. So do we do that or not? Well, yes, we do, because it's better to get $64 with item 2 than it is. So we actually are using this cell, which says don't use item 1, plus do use item 2. Okay, and then here, what happens? Here it's either the guy above or the guy 4 over. 1, 2, 3, 4. But this said, so don't use item 1 and then add in item 2. Yep, still works, right? Because item 2 only weighs 4 pounds. So we get 64.2. And then this cell, we look above and we go over 1, 2, 3, 4, still works. And now, but now when we fill this one in, it's the guy above because there is no 4 over. So we've only got 3 pounds to play with. So item 2 doesn't fit at all, so we have no choice but to use the guy above. And that's true all the way across. So those guys are all like that. Okay, so now let's move on, and again, to keep ourselves honest, we'll start in the far right instead of working up from the simpler cases. So in this case, we're either going to use 118 with items 1 and 2, or we're going to take advantage of item 3. But if item 3 weighs 5 pounds, so that's 8 minus 5 is 3. So we're looking at this guy. So it's either this guy or this guy. So 54 plus item 3 is worth 75. So 54 plus 75 is what, 129, I think? So, and yeah, and that beats the 118 above. So we're going to, is that right? 54 plus 75 is 129. Yeah, 129. So we're going to achieve 129, and we're going to do it with item 1 and item 3. Okay, and then in this cell, it's the guy above or guy 5 over. 1, 2, since I've got the indices, I can just subtract. Oops. So the guy above, sorry, so using item 3 gives us $75, right? And we don't get anything added over from this cell, but that's beaten by, so I'm going to erase that. That loses to the one just above. Whoops. Okay. So, and intuitively, what happened there is with 7 pounds, the 3 and the 5 don't work. So we revert to the previous one. Okay, so we're really close to the end here, so let's keep plugging away. So from column 6 over 5 gets us here, so that'd give us nothing plus item 5 for $75. Oh, that beats. Interestingly, item 3 all by itself beats item 2. And it wouldn't necessarily have to be true. Okay, and then one more in this row. We go over 5. 1, 2, 3, 4, 5. Still, oh, nope, that's what? Oh, I think I was counting wrong. Because when I was filling these out, I said it was use item 2 or not, so I only went over 4. Actually, it was going over 5. Because when you decide from one of these cells, if you decide to use item 3, you have to jump over 5 in the weight column. So anyway, so I needed this one, but that's 0, obviously. So if we use so with 5, we still have enough weight capacity to use item 3, and so we can still use it with $75, and that's all we needed. If we went any farther, we would no longer be able to use item 3 because we'd only have 4 pounds. Okay, so 2 more to do. So this one here. Okay, so we now need to do this guy. Whoops. Something terrible happened. Okay, not that terrible. So now we want to figure out this guy, and as usual, we're going to look at the guy above, or the guy, since item 4 weighs, I forget how much item 4 weighs. Just a second. Okay, let's finish this baby up. So now that I have the chart, I can see that item 4 weighs 2 pounds. So item 4 being worth 2 pounds means we look at this cell. 8 minus 2 is 6. So, and it's worth $26. So if we use item 4, we'll use this 75 plus 26, and 75 and 26 is 101, I guess. So we would get 101, So it turns out that the 129 beats that. And then similarly in this cell, apparently the 118 beats it, because if we go over 2, we're in this cell, which is 75, plus the 26 is not as big as 118. So this is 118, and now we're ready to move on to the very last cell, which is the only one we really wanted. So we look above, so we might be able to make $129, or we might, whoops, wait, what have I done? Oh, item 5 only weighs 1 pound. So item 1, so we go over 1 to this cell, so we have 118, sorry, item 5 weighs 1 pound. So we have 118 plus 12 is 130. So the 130 beats this 129, so our final answer is 130 using these two items, 1 and 2, combined with item 5. So that's our final result. We can use items 1, 2, and 5, giving us a profit of $130. So that concludes this little part of the video.